Hello and welcome. Um, Welcome to the Telesoft Technologies Next Generation FinTech Platforms webinar. First in a series of FinTech webinars that we're going to put out. My name is Steve Dodsworth. Just going to give you a bit of an overview and a bit of housekeeping. What we're going to cover today is that how we're going to show that Telesoft is well on its way to become a world leader in financial technology. We're going to show you some of the technologies and solutions and roadmaps that we're bringing to market over the coming months. These include hardware, cards, systems, IPs, and software. So we're going to go through those in terms of presentations and demonstrations today. A little bit of housekeeping before we start. Feel free to post questions in the chat. We're going to cover them at the end of this session, which will be about 30 minutes long. We won't be opening the audio, so I'll be reading out the questions. And thankfully, we've already got some questions in advance, so thank you to all of those who forward those. Delighted to say we have two of our top experts in the technology areas, one related to FPGA and technology, which is the head of engineering for FPGA, Richard Parks, and also Lee Hunt, who is our head of FinTech solutions. So although some of you may have known a little bit about Telesoft after we attended and presented at STAC last year, I thought it'd be a good idea on the next slide to show you a little bit about who we are and what we do. So if you look at this this chart, I'll probably start you on the right-hand side. There you can see some manufacturing. We actually manufacture our own hardware, including printed circuit boards that go and make up FPGA cards, PCIe cards, and so on. Also, we're involved in the cybersecurity world, and you can see here we actually run cybersecurity operation centers, and there's our facility in the UK. So going through one by one, you can see we're a UK sovereign company. We've actually got, because of our background in some cybersecurity matters, all our staff are security cleared. We've got over 35 years of engineering capability, working closely with telcos, governments, ISPs, and so on. We provide high-rate cybersecurity and network infrastructure solutions. And you can see the cornerstone of what we do in the middle there is high-rate, low-latency networking. We've got some great relationships with some major companies. If you look at the bottom of the chart, on the slide here, you can see some very recognized names that we've been providing technologies to as part of their networks for many years. We're also global. We have people and technologies and provided equipment and software across the world, all 6 continents. And each product is research, designed, and manufactured by our own engineering teams. A lot of capability there. And what we're doing with that now is providing a roadmap into financial technologies. So it's a unique pedigree, 20-odd years of experience. So I'm going to hand you over to the head of FPGA engineering, Richard Parks.
Hello. So yes, I'm Richard. Just going to introduce you to the Telesoft MPAC 7000 card, which you can see here. So the MPAC 7000 card is actually our latest in our line of PCIe hardware accelerator cards. Uses the Altera Agilex 7 I series FPGA. As Steve said, we actually design and manufacture our own hardware with ultra high throughput and ultra low latency in mind. The other benefit of designing and manufacturing our own hardware is that from a security point of view, you don't want to plug anything into your network that's untrusted, but we've got complete visibility and control of the supply chain, so there's no chance of any foul play. So on the left side of this card, you can see a pair of QSFP DD cages. These support 400 gigabit ETH. They can also support multiple 200 gig, 100 gig, 50, 40, 25, 10 gig, all of the standard network speeds. Again, as we said already, this card is designed specifically for real-time line rate, very high rate data processing. At the bottom of this card, you can see the PCIe Edge finger, which supports PCIe Gen 5, 16 lane. We use Altera's multi-channel DMA IP. And on the host side, we write our own drivers using DPDK, using kernel bypass. So we're going direct from DMA through to user space. Again, it's minimizing that latency, getting data from the card up to the host. We also support CXL by a pair of MDIO connectors that you can just about see to the right of the FPGA. There's 4 SODIMM slots, each supporting up to 32 gigs of DDR4, gives 128 gigs total. there is a daughter board, which isn't shown here, but we've got several QRNG chips or quantum random number generators, which can be used for private key generation, amongst other things. We've got extensive experience with encryption and decryption algorithms, including quantum-resistant AES 256 and elliptic curve cryptography, which could be used to secure inter-site communication links. I know there's been some talk at Stack over recent events talking of encrypting these finance links. So there's options. From timestamping point of view, we do support PTP, Precision Time Protocol, and we have a PPS clock input to sync up to a PTP Grandmaster. We currently support nanosecond resolution timestamping, but we do have work underway to hopefully achieve picosecond resolution. And finally, we are working in collaboration with a partner to implement FPGA accelerated AI inference engine. And the Stack benchmark has shown that that's 10 times lower latency than a GPU. So we're now going to go on to demo setup. So I'm going to show a demo of our OPRA Decode at 400 gigs. Just to talk you through what I'm going to show you first. So at the bottom here on the left, there's this OPRA test generator. This is using one of the MPAC 7000 cards I've just explained. This is taking a OPRA feed from multicast that we captured last August. And we've essentially taken those packets, squeezed them together, sped them up and looped them to kind of generate this synthetically saturated 400 gig OPRA feed. We then take that over OM4 fiber into the second MPAC 7000 card, which is running our OPRA Decode engine. So inside the FPGA here, we receive the packets in our 400 gigabit ETH MAC. We do packet classification, VLAN removal, IP extraction. We then go on to this full line rate OPRA Decode. So we're opening up the block and decoding every single message inside it. We then go through to this runtime configurable OPRA message filtering, which I will show you in a couple of minutes. And then those filtered messages or the messages of interest are sent up to the host using this NCDMA PCIe over Gen 5. So hopefully we're now going to play the demo. I recorded this about an hour ago, so we'll have a look. Hi, I'm going to demonstrate Telesoft's 400 gig OPRA processing capabilities. I'll start by explaining our dashboard. So the first three panels here are rates per second. This first dial is the bandwidth received into the 400 gigabit ETH MAC. The second dial is the number of IP packets received per second. And this third stat is the number of OPRA messages received and decoded per second. The top right panel here is aggregated counts or running totals. So the total amount of data received into the system, the total number of IP packets received, and the total number of OPRA messages received and decoded. The two graphs below again are aggregated counts. So the count of OPRA messages received by participant ID and the count of OPRA messages received by message category. Now we have a demonstration app running to receive the stats and sample decoded messages, which will be visualized in this panel below. This is all in Grafana, so if you want some different visualizations in your own application, that is certainly possible. This is wrapped inside Telesoft's proprietary GUI as an embedded frame. Or if you've got no visualizations at all, you can simply use the REST API or command line interface. Now I'll start our 400 gig OPRA feed. This was data captured from an OPRA multicast last August. Essentially, it's been sped up and looped to synthetically generate a saturated 400 gig OPRA feed. Now, all messages in this feed are short equity and index quote messages, but we do also support underlying value messages, equity and index last sale messages, open interest messages, equity and index end of day summary messages, and long equity and index quote messages. Now we can see that we're ingesting a sustained 335 gigabits per second, about 335 million IP packets per second, and 629 million OPRA messages decoded per second. So let's take a look at the filtering options. Before we do, from the participants graph here, we can see that NASDAQ BX options are sending the most messages. So we would filter them out just to show the capabilities most clearly. So filtering out NASDAQ BX options. So at the moment on the filtering options, we can filter by participant ID or by message category. We can obviously do more complex filter setups. If there is a bespoke filter or some sort of pre-processing step you're particularly interested in, please do come and speak to us. And if we go back to our dashboard, we can see the NASDAQ BX options is now flatlined, indicating that no more messages from NASDAQ BX options are being sent up to the host. Now, the benefits of decoding the OPRA messages and filtering in the FPGA are that we're reducing the bandwidth sent to the host. This is reducing the software processing of any OPRA messages that ultimately are going to influence your trading decision. And this reduces your latency. The benefits of this solution over a NIC card or a smart NIC is that we're stripping off the ETH headers, any VLAN, any IP headers and UDP headers, and we're passing the OPRA block itself and sending up fixed format OPRA messages and only the messages that are going to influence your trading, rather than the software having to process through, deserialize the OPRA messages, only to find out you didn't need those messages in the first place. Now, in the FPGA, all of the OPRA decode and filtering is performed in parallel, so it's fixed latency regardless of the ingress traffic profile. So just in summary, in the last few minutes, we've received over 5.2 terabytes of data, over 40 billion IP packets, and decoded over 81 or 82 billion OPRA messages. So this is full decode with the runtime configurable filtering and all the messages presented to the host in a 64-byte fixed format for efficient host processing. Thank you. Okay, so I hope you found that useful. If there's any questions, please ask them in the chat, or you can email them to webinar@telesofttechnologies.com, and I will answer them at the end. I'll now pass over to Lee to talk about the Fintech Observability platform.
Hi. I will now give you a brief overview of the supported functionality on the Telesoft Fintech Observability platform. The platform runs on a latest spec Intel 4th Gen Xeon 6430 server and supports up to 4 MPAC 7000 cards configured with either 400 gig or 100 gig inputs. So that's an impressive 16 individual 100 gig inputs all going into one server. The FPGA on the 7000 card supports P2P timing and applying nanosecond timestamps to the received packets. The programming of the FPGA allows the platform to support generation of flow analytics and real-time detection of microbursts and gap detection for market data protocols. We'll now move on to the next slide, which shows the setup of the demonstration of the observability platform. The demo setup comprises the platform receiving high-rate traffic over 4 100 gig ports from another server which is generating the traffic. For the platform, the FPGA on the MPAC card is programmed to support float-safe load balancing of metadata packets and microburst and gap reports output across to the 20 DMA channels. The software on the host supports multiple DPDK worker threads to support processing of the reports and metadata packets from the DMA channels. For the high-rate traffic simulation, we're using another server equipped with an Intel 100 gig NIC and using T-Rex in stateless mode to generate the traffic. With this approach, we can support different profiles for market data protocols where field insertion is used to set increasing sequence numbers inside the UDP payload in the packets. Now I will show you a recorded video of a live demo of the platform in action. Today, I will be showing you a live demo of Telesoft's Fintech Observability platform, where we will be simulating a data center receiving high-rate traffic over 4 100 gig ports. For this demo, the FPGA and the Telesoft MPAC line card has been programmed to enable 1 millisecond interval microburst detection, flow analytics, and market data real-time gap detection on a per flow basis. I'll now go through the UI screens with you. This first screen, the live overview screen, is a really important one as it obviously gives you a snapshot of the current status of the system. As we can see on the left hand side here, we have port gauges which give the overall traffic rate coming into each of the ports. Alongside that, we have a protocol breakdown where per market data protocols, we have the overall rate there. The FPGA has currently been programmed to detect OPRA, pitch and XTP protocols. Underneath this, we have an active flows time series graph, so we can see the number of flows that are coming into the system. Alongside that, there's another time series graph, which shows the rate on a per flow basis, a pie chart, which does the same. And also, quite importantly, in the top right-hand corner of the screen, we have counters for gaps and microbursts when they're detected. So if you're in this screen and a microburst or a gap is detected whilst you're in this screen, you'll be alerted to it straight away because you can see the counts going up and the graph over time showing that activity has occurred. Next screen I'll show you is the port status. So as you can see here, we've got gauges on the left-hand side showing the rates coming into the platform. On the right-hand side, we've got time series graphs showing the traffic rate. So you can see there's quite a high rate of gigabits per second coming in with the traffic fluctuating. The next screen is the Microburst analysis screen. So in here, we get alerts coming out every time a microburst is detected. If we click on the show actions button there, then we get a breakdown coming up at the top of the screen here. And then we also have the flow reports that were for the same time period when the microburst occurred, so we can then correlate and look through the activity on a per flow basis to see what was happening when a microburst occurred. The final screen I'm going to show you is the market data analysis screen. So this again is where we get alerts for when gaps are detected in market data protocols. So if we look here, we can see that we detected an OPRA protocol and there's a gap of 6. So that means there's a packet where we had the sequence number for the packet before, and the one after it showed that there was a gap of 6 numbers in the sequence numbers. Also on this screen, we have a market data flow status report. So this is where over time we have counts for the flows, so we can see what number of gaps, and we can see if there's reset. We can check for latency to see differences between the receive time and the position timestamp values that are inside the packets. Okay, so now I'm going to go through this roadmap slide. So for latency monitoring, the platform can support checking the packet's receive time on the wire against either the previously added hardware timestamp from things like switches or packet brokers, or the seconds and nanosecond timestamp values which are contained in market data protocols. For microburst analysis, the platform can support doing detailed analysis on a per flow basis to identify what the most busiest flows were during the microburst event. This is obviously really useful for link capacity planning. For TCP flow analysis, the platform can support monitoring of retransmission timeout, round trip times, and window sizes. These are the sort of things that can be used to explain failed order executions whilst trading. The platform is also actively being worked on now to provide greater market data protocol coverage so that the real-time gap detection can be supported for multiple different organizations and their protocols. We're also looking at supporting entity tagging, where related entities can be grouped together by IPs and domains where they're all associated together. Finally, the platform will also support longer-term historical analysis with flows and reports stored in Elasticsearch. So that ends it from me for now, talking about the roadmap. I will now hand back over to Steve again.
Thank you very much, Lee. So just to summarize here, before we move on to questions, I hope you've all got your questions ready. Just to summarize what you've seen from us and what you're going to see us over the coming rolls out in this technology. You know, the headline there of 400 gig processing, full line rate with 0 packet drops. We have a very, very extensive experience in high performance FPGA design and providing SDKs and services for that. Also, we have the intellectual property blocks, such as the OPRA Decode engine. This is one of the first ones we've released, but as you can see, running that at 400 gig has huge challenges from engineering standpoint and performance standpoint. Our advanced FPGA PCIe boards are designed in-house, custom made for the use case. And as you can see, we're adding some very, very interesting features on top of, like quantum cryptography for securing the data. We're clearly an engineering-led company. We have a lot of solutions in the field, which a lot of people have helped customize with us, because we know that particularly the financial industry, there's a lot of value to shave off a few nanoseconds. And I think this is one of the things we want to share with you, is we're very open to having conversations about doing tailored solutions for your specific use case. The products are designed with very, very timing accuracy, and and we're looking at picosecond now, ultra high throughput, low latency engineering. And one of the new areas we're looking at, as Richard mentioned, is we're looking at AI and machine learning, FPGA inferencing engines to particularly for the inferencing of quantitative trading, but there are obviously other areas where we can use very, very high performance AI for multiple use cases. Right, next slide, we're going to move on to just going through Q&As. I'll kick us off with some of the questions that thank you for emailing through webinar@technologist.com. But you can see there on the chat. By all means, add to that now. So what have I got here from the first caller, shall we say? Why does the OPRA Decode demonstration not show 400 gig? Good question. I think I saw something like 350 in there. Richard, over to you.
Yeah. So this is kind of as part of the Mac. It's the same with 100 gig Macs. So if you're used to using a 100 gig Mac and you've got a 64-byte interface, if you're sending 65-byte packets, you've got an awful lot of wasted space, and that means that it's very unusual that you'd be sending exactly 64-byte or 128-byte packets all the time, and that's the only way you can actually achieve 100 gig throughput. It's exactly the same when you go up to 400 gig. So the interface is slightly different, but ultimately, if you're sending not powers of 2 size packets, then it's very unlikely that you achieve that full 100% line utilization. So 335 gig, I think it was just the speed that the packets I grabbed from the OPRA multicast happens to be. So that's all it is.
Okay, good answer. I think there's another follow-on question. We're talking a lot about latency and the use cases here for obviously for algorithm trading. What was the latency measurement on the OPRA Decode engine, and how was it measured?
Okay, so the latency through the OPRA Decode itself is about 125 nanoseconds, measured from the packet, the clock cycle that the packet was received from the Mac to the clock cycle that the packet was sent out over PCIe. So it's pretty quick.
Okay, I've got another question here, probably more for Lee. In your demonstration, why did you select OPRA, Pitch, and XDP for your platform? Will you support any other protocols? I think there are quite a few protocols out there. So,
yeah, sure. There's obviously lots of organizations out there, 20 plus with all different protocols. Yeah, we just initially selected the OPRA, Pitch, and XDP protocols because they were some of the most popular and common ones that are in use at the moment, and a lot of other protocols are very similar to those. So, it's easy for us to then look at implementing other protocols as well.
Follow-on question: Where would you get your test data from? Where did you get your PCAPs from, basically?
So yeah, we just got our test data PCAPs from a friendly exchange. So yeah, so we've got samples of lots of different protocols that we've used to develop the product.
Good. Okay, next one in. I just got one here for back to Richard again. How does latency change with ingress of traffic rate?
Oh, okay. So because the way that the FPGA naturally works, everything is done in parallel. We have natively parallelized and pipelined the OPRA Decode and filtering. So it doesn't matter what you throw into it, that latency is completely fixed. So we've got 400 gig in from the Ethernet port, and we've got 400 gig out from the PCIe Gen 5. So yeah, we are solid. It doesn't matter what you throw at it, it is completely fixed. Yeah.
Very good. I've got a kind of semi-commercial question here. So what are you offering to the market? What are you selling? Well, I can handle that. We have the MPAC 7000 card, the latest and greatest 400 gig dual 400 gig solution that you're seeing on the demonstrations. We're also on top of that card offering SDKs and also IPs such as the OPRA Decode engine you saw in the demonstration. And what Lee showed you was a system where we put 4 of those cards in a 2U chassis, and that enables you to implement multiple solutions, and that will and the demonstrations of all the gap detection, latency measurement, microburst analytics, and so on is part of that solution. Now, there's clearly lots of other things we may put, as Lee showed you on the roadmap. There's lots of other things that we're going to actually implement in that solution over time, and yeah, we're offering out that conversation now with each and every one of you. If you've got a use case that you would like a conversation of, like pointed out that we do tailored solutions and integrations, we'd love to have that conversation with you in the coming days and weeks. So please reach out. I've got another question in on the chat. Thank you. How do you ensure no packet loss? Do the number of packets in your synthetic data set, assuming the data set used is synthetic?
I'll grab that one if that's all right. So yes, you're absolutely right. The data set we're using for testing is it's real data, but we have synthetically looped it and manipulated it a bit just to really stress test the application. We can guarantee there's no packet loss because you think back to the Telesoft's heritage has come from the very high rate cyber sort of world. So we've been handling multiple 100 gig and 400 gig connections for a long time. Our FPGAs have always been written with that in mind, and particularly in cyber, just the same in finance, you can't miss a packet. You should guarantee the packet that you miss will be the really important one that's low. It's a trade or it's something really bad on your network that you need to be aware of. So our whole legacy, all of our code is written that we absolutely guarantee that we're not dropping anything. And that's been the way for decades. So we've kind of always done it. We've always done it this way. So I hope that answers your question.
Very good. Thank you, Richard. Yeah, I think that looking at the time, I think we should probably wrap up now. Just one probably slide to show you at the end here. We'd love to hear from you. Thank you for attending. We put that webinar at telesofttechnologies.com in the chat. We can do that. We can reach out to me personally. We'd love to have a conversation with you. Thank you for attending. It's been very, very good to have so many of you engaged with what we're doing. And for that, I will close the webinar. Thank you very much.